Hello again in DOS. So the last time I was making a tiny program that would make its own interrupt handler. There is a mistake in this program. I need to point it out now. I should have added a segment prefix here, because I have changed the DS register, so I can no longer use normal data storage through DS register, but I can still access variables in my own segment, like this one, through CS prefix. Now you might notice that this is in fact another demonstration how before protected mode everything was freestyle and dangerous. This small mistake caused us to write to some memory in 0 segment, most probably some BIOS variable. So we have overwritten some BIOS variable and did not even notice. We've been running this program and nothing happened, nothing bad happened. But it could. And these kind of bugs were especially dangerous. You could not notice right away that you are overwriting some not your own memory of another program or DOS or BIOS. And then one day your program that seemed to be working would suddenly overwrite variable in a critical time when it really happened, when it really breaks something, and you would have an unexpected problem, serious bug, not noticed earlier. So we have inadvertently demonstrated how a DOS program could silently overwrite some BIOS variables and not even notice. Yes, this would be very hard to debug properly. We could also use ES prefix here instead of CS, because in DOS.com program like this one, all segment registers are set up to be the same value of the segment of program. Well, with MZ executables it is similar. But the program segment that is set up, this is the segment that starts with program segment prefix. This 256 bytes here. And in case of MZ executables, segment of PSP is usually not the segment you would like to have set up. When we move on to writing some more complex executables, then I'm going to demonstrate this in detail. As for now, let's do some further experiments with interrupts. Well, our program now is very tidy. It restores the vector before returning back to DOS. But as we have noticed earlier, program can set up some vector and not restore it and just go back to DOS. And because memory of program is now no longer in use, DOS could write something in this place, overwrite the interrupt handler, and everything would break apart. But we could think that perhaps if program managed to set up its interrupt handler in some kind of memory that would not be overwritten soon, then a program could this way modify some interrupt vectors and return to DOS and silently keep doing something strange in interrupt. And this is in fact a technique that was not a technique used by some obscure applications or malware. It was in fact a regular technique for writing many kinds of DOS drivers or some applications that you could use in background. This technique was called terminate and stay resident. So return back to DOS, but leave something in memory. Let's take a look at some documentation. Ralph Brown's interrupt list. The best possible reference you might use for DOS and BIOS of these 16-bit days. We have this function. It is very similar to function 4C, which returns to DOS with return code. But this time we also have additional parameter, number of paragraphs to keep resident. What does it mean? Paragraph was a data unit used in those days. This was in fact granularity of segments, 16 bytes. So paragraph was an offset where a next segment would start. And when we talk about number of paragraphs to keep resident, this is number of paragraphs starting from PSP. So PSP is already 16 paragraphs. And we need to keep a bit more in memory. Enough to keep our exception handler, interrupt handler in general, in memory. Let's save it as a new source, so we do not overwrite previous one. I want to make some experiment with clock, so let's call it clock. We are going to use this function. This way I'm setting up number of function and return code 0 at the same time. This is going to be number of paragraphs. And now for the interrupt. I do not need this option. Oh well, let's start simple. I would like to take over clock interrupt. This is the interrupt that is automatically invoked 18.2 times per second, and it updates the clock variable in BIOS memory. We have seen it the last time. The clock interrupt is one of so-called IRQ interrupts. In addition to exceptions, we have already seen an exception 0 last time. There are also interrupts that are caused by some external source, not by an error within processor, but by some external device like external clock or keyboard or mouse or other device. When it wants to tell something to our CPU. For example, someone has pressed a key, so keyboard has some data to give to our CPU about the key that was pressed. And clock, external clock, just keep knocking to CPU 18.2 times per second. IRQ 0 is clock. IRQ 1 is keyboard. We may play with both of these. And IRQs are first processed externally by something called programmable interrupt controller. And this controller can be set up to map external interrupts, IRQ 0, IRQ 1, and so on, to actual interrupts processed by CPU. And in old those days, this was mapped to interrupt 0. IRQ 0 was mapped to interrupt 8, IRQ 1 to interrupt 9, and so on. This was not a good choice, because later CPUs like 386 used the same interrupt numbers for some exceptions. So then you had interrupt that could be caused either by exception in CPU or by external event, IRQ. Then your handler needed to do some additional checks to find out whether the interrupt was exception or IRQ. For example, I had this program with interrupt 13, which is IRQ 5, I think. And this was general protection exception that I needed to handle when I was setting up flat rear mode, for example. And there I had to distinguish whether this was IRQ 5 or general protection exception truly. I may one when they show this, when I show how to enter flat real mode. But this is a story for another session. For now, we are going to focus on IRQ 0. A single vector is 4 bytes, a far pointer, so we skip 8 of them to set up vector for IRQ 0, which is interrupt 8. Now, another important detail is that we need to first disable interrupts and then enable them again. Why is that? It's because we modify vector with 2 different instructions, and between the first one and the second one, the vector is not completely set up. So if CPU tried to execute this interrupt, for example, in this place, and remember, interrupt like clock interrupt may happen at any moment, then vector would be not completely set up. It would have offset replaced already, but segment not set up yet. And then it would most probably crash, jump to some strange place in memory, unexpected. Therefore, we disable interrupts by clearing the interrupt flag. We set up new vector and re-enable interrupts by setting the flag back. Now, we could just return from interrupt. There is a special instruction for this, I read. However, this is not a plain interrupt, this is an IRQ, and it requires additional special handling. We need to tell interrupt controller that we have handled the IRQ already. Because remember that interrupt controller is something external to CPU, so it does not know that interrupt has already been executed. So if we did nothing here, interrupt controller would kept waiting for CPU to process the interrupt, and it would never issue another IRQ. Oh, interrupts that happen when there is CLI. Well, exceptions happen anyway. This does not disable exceptions. This does disable external interrupts like IRQ, and they simply wait. Until we tell interrupt controller that we have handled the IRQ, it is going to nudge our CPU that it should handle this interrupt. And CPU is going to think that it has already called the handler, so the job is done. So to avoid this impasse, we need to send something to interrupt controller. Sending this value to, this is the base port of first interrupt controller, There are two interrupt controllers, but let's leave it at that now. And of course we need to preserve any register that we use, because clock interrupt may happen at any moment. Well, any IRQ may happen at any moment in the middle of any program doing something. So we need to preserve any registers so that we do not trash registers that program is using. Let's mark end of resident as a label and calculate resident paragraphs. We should round it up to 16 bytes up and then count the paragraphs. This should do the job. And before we test this, I'm going to leave that assembler because this IDE works in protected mode, so interrupts may not happen exactly like normally in DOS. We are going to assemble it in a classical way with FASM from command line. And let's try it. Please notice that clock in upper right corner has stopped. We have replaced the IRQ0 handling, so this IRQ no longer updates the clock variable in BIOS memory. Oh, if we run memcopy from the last time, we can now see that nothing moves. I can press Shift and it's visible, but the clock is not updated anymore. So, well, what can we do now? We could perhaps update the variable on our own. Let's preserve the ES, then set up the ES. Maybe this way this time. And then increase value of clock. Well, perhaps because this is 32-bit value in fact, but I do not want to use 386 instructions right now. So let's do this in 2 instructions. And then with carry to the upper word. How do I know this magic value? We could look it up in Ralph Brown's resources too. There is a file with memory map. This is the clock. It is in segment 40 at offset 6C. But the way segments work, as I have already said, every next segment starts after a paragraph 16 bytes. So difference between two segments is 16 bytes. So to calculate physical address, you just multiply number of segments by 16 and add offset. If we multiply this by 16, this is then 400. We add 6C, we have 46C. This is the physical address of this. And because this address is still smaller than 16-bit range, we can access it from 0 segment. Like here. Okay, let's see if this restarts the clock. Yes, clock is running again. Now we could do something silly and just make clock run faster. Let's say five times faster. This is the effect. Back to normal. Now, we have run this program several times, and every time it was leaving a copy of itself in memory. We can see 4 copies here. Only the latest one is working, because every time it just replaces the interrupt vector. So yeah, we would run out of memory in the end. This is not much, it's 300 bytes for every copy. So we would not run out of memory soon, but we would run out eventually. So yeah, we were storing previous vector, but the way we have written these programs, it is not easy to recover it now. A TSR would normally handle some additional interrupt and provide a function in that interrupt that another program could call to uninstall this TSR from memory. Let's make another copy and try to make a good TSR out of it. Oh, I was also leaving stored vector outside of resident range, in fact. Let's now take it all and move to the beginning of program. Because this installer code does not need to stay in memory. This is the entry point of program, so we need to jump to installer code. And now when we terminate and stay resident, this is going to get freed. Only this part is going to stay in memory. And we are going to add some additional function. Let's say let's choose some interrupt number that is not very likely to be used by other tool, like 99 hex. This is an interrupt function, so we need to do iRead. This is going to be manually called interrupt, so we do not really need to preserve registers this time. Again, we need to disable interrupts until we set up the entire vector. And here we should also free memory. I would have to look it up, I do not remember the function. But let's first check if it works. At least restoring the vector, interrupt vector. So let's use a faster clock and then try to restore it to regular. Okay, we have a faster clock now. Oh. When I don't do this, Fasm does not know what extension to give it. Oh, it seems I managed to break something anyway. Let's try a different number. Oh wait, I see. Why do I use CS here? What was I thinking? We can probably go back to 9.9. We were not setting up vector properly. And now... Great, it restored the clock. So I have found the bug, but we should probably end now. So let's leave it to a next session to improve this TSR, because right now it restores the clock to the previous state, but the clock interrupt vector to its previous state, but it does not free memory. Also, we call this function to for the program to uninstall the clock handler, but we need first a reliable method to detect whether TSR is already in memory, because we cannot simply call this function when our TSR is not in memory. So there is still a lot to do to make this a proper TSR program. But at least for now we are able to see that we can speed up the clock and then restore it. This is all for today. Thanks for watching. And